Hello and welcome. In this video I want to show you more examples of checking continuity of a function at the given point. The first function is f of x equals to x to the 2 minus x if x is less than or equal -1 and f of x is 2 to the power of x when x is greater than -1. We are given this function and we are asked to check the continuity of this function at -1. Before doing this example, let me remind you the definition of a continuity of a function. Let's say we have function f. F is continuous at a. In this example, a is -1. F is continuous at number a if the following three conditions holds for the function f. F of a is defined. This is the first condition for continuity of a function at a point. The second condition is that limit of the function f of x when x approaches a, which means that the left limit and right limit should be equal to each other. And finally, the third condition is limit of f of x when x approaches a must be equal to f of a. So f of a, which is the value of the function at point a, should be equal to the limit of the function at point a. If these three conditions is satisfied by the function f, then we say a function f is continuous at a. Now let's do this example. Attention, in this example, the point a is -1. So we want to check the continuity of this function at -1. We start with the first condition for continuity. Let's see f of -1 is defined or not. So we want to check for this function, is f of -1 defined or not? If you look at the equations of the function f, when x is less than or equal, attention, or equal to -1, we have to use this rule for function f of x. So for finding f of -1, I am going to use this equation. So f of -1 would be -1 to the 2 minus -1. -1 to the 2 is 1, minus 1 is also 1. 1 plus 1 would be 2. So as you can see, f of -1 is 2. So the first condition for continuity is true and is satisfied by the function. Let's see, is the second condition also satisfied or not? For finding limit of this function when x approaches -1, we cannot find the limit at one step. We have to find limit of f of x when x approaches -1 from the right and limit of f of x when x approaches -1 from the left separately. Why we have to do so? Because when x is less than -1, you have one equation, but for greater than -1, you have another equation. So we cannot find the limit, the two-sided limit directly. We have to split the limit to right and left limits, like this. For finding limit of f of x when x approaches -1 from the right, which equation we have to use? The top one or the below one? When x approaches -1 from the right, it means that x is close to -1, but it is greater than -1. So we have to use the below equation, this equation, for finding this limit. So this would be limit of 2 to the power of x as x approaches -1 from the right. If you simply plug in -1, it would be 2 to the power of -1, which is 1/2. For finding the left limit, we use the other equation. Limit of x approaches -1 from the left of x2 minus x. Simply, if you plug in -1 for x to find this limit, -1 to the 2, like here, would be 1 minus -1 would be 2. So the limit is 2. The left limit is 2. The right limit is 1/2, because the left limit and right limit are not equal to each other. What we can conclude from this? That the limit does not exist at -1. Because we know that a limit in general exists if the left limit and right limit are equal. So limit of f of x when x approaches -1 does not exist. And we don't need to check the third condition for continuity. From here we say, because f of x, limit of f of x when x approaches -1 does not exist, so immediately we can say f of x is not continuous at -1. But before I show you the next example, let me tell you something. Attention to here and here. As you can see, the left limit of f of x when x approaches -1 is equal to the value of the function at -1. Because the left limit is equal to the value of the function at -1, this is true that f is not continuous, but we can say that f of x is continuous from the left. So let me explain this again. When a function is not in general continuous at a point, it can be, but it can be continuous from the left or from the right. In this case, because the left limit, as you can see here, is 2, and the value of the function is also 2, so this function is continuous only from left at -1. Here we are given this function f of x is given by these equations. 3x minus x2 when x is less than equal 1. When x is greater than 1 or less than 4, so when x is greater than 1 but less than equal 4, we have this equation x plus square root of x, and when x is greater than 4, the given equation is this radical x2 plus 9. So we are given this piecewise function and we are asked to check the continuity of this function at the points 1 and 4. Why we are interested to check the continuity of this function at 1 and 4? Because as you can see, this function is piecewise at 1 and at 4. That's the reason we are interested to check the continuity at these points. As usual, we start with the definition of the continuity and we start with the first step, which is checking to see if f is defined at the point or not. We start with point 1. So we want to check the continuity of this function at points 1 and then 4. First we start with point 1. Let's see if f of 1 is defined or not. As you can see from here, when x equals or less than 1, use this equation. So 3 times 1 minus 1 to the 2 simply would be 2. So f of 1 is defined as is 2. Now we have to check the limit of this function when x approaches 1. Once from the right, once from the left. And you know why I am doing the limit like this, because I cannot find the limit right away, so I have to find right limits and left limits separately. For the left limit, I'm going to use the first equation, 3x minus x2. Because when x is less than 1, we have that equation. So limit of 3x minus x2 when x approaches 1 from the left. But when x approaches 1 from the right, I'm going to use the other equation, x plus radical x. Why we use this equation for finding this limit? Because when x is greater than 1, use that equation. And you can find both of these limits simply by substituting number 1 in each of them. The first limit would be 1 plus radical 1, which is 2, and the second limit is simply 3 times 1 minus 1 to the 2, which is 2. So as you can see, both of these limits are equal to each other, and they are 2. So from this, immediately we can conclude that limit of f of x when x approaches 1 exists. So the second condition of continuity, if you look at here, the second condition of continuity is that the limit should exist. So the second condition is also satisfied by this function. Finally, we have to check the last step. What was the last step? The last step is to check to see the limit is equal to the value or not. The limit exists and it is equal to 2. And the value is also 2. So the third condition of continuity, which is limit of f of x when x approaches 1 should be equal to f of 1, is also satisfied by this function. Again, why this is satisfied? Because this is 2 and this is also 2, so they are equal to each other. And because all the condition is satisfied, we can conclude that f is continuous at number 1. Now we want to check the continuity at 4, at the second point. First, we have to start from f of 4. For finding f of 4, which equation we have to use? This equation. When x is equal to 4, we have to use this equation. So I'm going to plug in 4 here. So it's going to be 4 plus radical 4. So we have 4 plus radical 4, which is 6. For finding the limits, we find limit from the left and we find limit from the right. For finding the limit from the left, I am going to use the second equation, x plus radical x, as x approaches 4 from the left. Why? Because, look at this, when x is less than 4, use this equation. And when x approaches 4 from the left, x is close to 4 but less than 4, so we have to use this equation to find the limit. For finding the limit from the right, we use this equation, radical x to the 2 plus 9. So this would be limit of radical x2 plus 9 as x approaches 4 from the right. The first limit simply is 4 plus radical 4 is 6, and for finding this limit also we can substitute 4 for x. Direct substitution works. It would be 4 to the 2 plus 9, 25. Radical 25 is 5. Here, the function f is not continuous. Why? Attention, the left limit and right limit are different at point 4. The left limit is 6, the right limit is 5, so the function is not continuous because the condition for continuity is that the limit should exist, but the limit of the function f of x when x approaches 4 does not exist. So immediately here we can conclude that from this we can conclude that limit of f of x when x approaches 4, this limit does not exist. And because this limit does not exist, we conclude f is not continuous at 4. So, f is continuous at 1, but f is not continuous at 4. Before we jump to the next example, let me tell you what is the type of discontinuity. F is not continuous at 4, so F is discontinuous at 4. But what is the type of discontinuity at 4? When left limit and right limits are not equal to each other, the type of discontinuity is a jump discontinuity. Attention, both of these limits exist, but they are different. So at point 4, we have a jump, because when we approach 4 from the left, we approach to 6. From the right, we approach to 5. So at 4, a jump happens at the function f. And so the type of discontinuity, f, has a jump discontinuity at 4. Now let's do the next example. We are given this function f of x equals to mx to the 2 plus 4x when x is less than 2 or equal to, and if x is greater than 2, 4x to the 3 minus mx. But what is the question? We have to find a value for m, find m, such that that value makes f of x continuous everywhere. So let's review the question again. We have a piecewise function, but this is a bit different function than the previous examples. Look at the given function. We have variable x, which is the variable of the function. Always we have x. But m, what is m? M is an unknown. We have to find m. That value of m makes f of x continuous. So basically this function is not continuous, but for a particular m, for one specific value for m, we can make this function by that value continuous. What is that value for m? When we look at this equation for f of x, what we can see is that when x is less than 2, we have one equation, and when x is greater than 2, another equation. So this function is not continuous at 2, but we want to find m that makes this function continuous at 2, and then f is continuous everywhere. So basically for this question, the number that we have to check continuity at that number is 2. So similar to the previous questions, we start with f of 2. F of 2 would be equal to m times 2 to the power of 2 plus 4 times 2, which is 4m plus 8. But we know that for continuity, we have to find right limit and left limits. For finding the right limit, we have to use the second rule, which is this. Because x approaches 2 from the right, x is greater than 2, so we are going to use this equation. But for finding limit from the left, we are going to use the first equation, mx2 plus 4x. X approaches 2 from the left, here x approaches 2 from the right. If simply you plug in 2 for x, 2 to the 3 is 8 times 4 is 32 minus 2m. For finding the second limit also, if you simply substitute 2 for x, it would be 4m plus 8. Now remember definition of continuity of a function at a point. A function is continuous at a point when the limit exists at that point. Back to this question. Limit from the right is 32 minus 2m, as you can see here. Limit from the left is something different, but we want to find m To make the function continuous, the right limit and left limit should be equal to each other. So, because we want to find m to make this function continuous, the right limit and left limit should be equal to each other. Then the limit exists. By setting them equal to each other, we can find simply the value for m. If you rearrange this equation, if you move, for example, 4m to the left, or subtract 4m from both sides, and if you subtract 32 from both sides, simply you can see that negative 6m would be 8 minus 32, negative 24. And from this, if we divide both sides by negative 6m would be 4. So the value of m that makes this function continuous is 4. To check that this number really works, simply, if you plug in 4, if you plug in this number 4 here, and also here, and here, you can see that all of these values are equal to each other. And this shows that this number makes the function f continuous. I hope you liked this video, and see you in the next videos.